far in this class, we've only studied robot kinematics. That is, we only worried about the positions and the velocities. Now we're ready to move on to dynamics. Here's where we're going to study the forces and the accelerations. In the last lecture, we started to talk about forces, that's statics, and there we were able to relate the force and moment of the end effector to the forces and torques on the joint variables through the transpose of the Jacobian. Here, we're now going to start worrying about the accelerations, and we'll bring in the force relationships through the Jacobian at the end of the lecture. Now let's look at some force balances. We know from Newton's second law that force is equal to mass times the acceleration. Another force that acts on the system is the drag force, and typically it's proportional to the velocity of the system. Another kind of force is a spring force, which is proportional to the displacement of your system. This is Hooke's law, where force is equal to negative k, the spring constant, times your displacement. Now, we can look at a simple system. Let's take a mass spring system where we're going to balance the force due to inertia with the spring force. When we do that, we end up with this nice equation of motion. We can make it look a little bit better where we substitute in for a square root of k over m, this omega naught. This you'll see is the natural frequency of the system, and this is the resulting equation of motion. Now, once you have this equation of motion, you're probably wondering, what do you do with it? We have to find a solution for x of t. Solving differential equations is a whole topic onto itself, and in this class, we're not going to expect you to solve differential equations. What we will do is we're going to provide you a solution to this differential equation, this second order differential equation, which is simply your function x of t is a sum of a cosine plus a sine term. Now, the fact that this is the solution to this differential equation really shouldn't surprise you, because what you have here is a function is equal to its second derivative, more or less. And what functions are equal to its second derivative? Well, sine and cosine are both equal to their second derivative, minus some constants that we would have to hunt for. Now we're going to add on to the mass spring system by introducing this dash pot, this damper. Recall, when we do the force balance, that force is linearly proportional to the velocity of the system. So when we do our force balance, the resulting differential equation looks like this. Now, once again, we're not going to expect you to solve this differential equation. What we are going to do is give you the form of the solution. Now, again, we'll make a substitution in for natural frequency, and we're going to make this other substitution that we call damping ratio, so the second order differential equation has this form. So this second order differential equation has three solutions: critically damped, overdamped, underdamped. Overdamped is the solution where the mass is in honey and its drag is really high, so the mass moves slow. Underdamped is that there's very little resistance to the mass, so it's able to come in and overshoot the solution. Critically damped is the solution that's just right. A little bit more damping, and you'll be overdamped. A little bit less damping, and you'll be underdamped. I remind you, if there's no damping in the system, then our response is just this oscillatory answer here. The mass goes back and forth forever. Let's look at the underdamped solution. The underdamped solution, x of t has this form where we have an exponential and the sum of a sine and a cosine. This portion of the solution corresponds to the harmonic component of the answer. This portion of the solution corresponds to that harmonic decaying. So you end up with something that oscillates and decays. In other words, its amplitude goes down to 0. The oscillation isn't the natural frequency. It's actually the damped natural frequency, which has this term like so. The next solution is overdamped. That's when your damping ratio is greater than 1. The picture, again, the mass is like in honey. Here, you have a very slow response to get to your solution. And then finally, we have critically damped. That's when your damping ratio is equal to 1. A little bit more damping, you'd be overdamped. A little bit less damping, you'd be underdamped, and there'd be some oscillations. In some ways, you can think of this as the quickest way to get to your solution or to settle down to zero. To derive these equations of motion, you could use your notions of force balances, but that can be really tricky. So we're going to use the Lagrangian approach. I remind you that Lagrange was born in Italy, but he did die in France. And the Lagrangian is this difference here where T stands for kinetic energy and V stands for potential energy. So this is the difference between kinetic energy and potential energy. It's sometimes tempting to think that we're going to do something with conservation of energy. In other words, T plus V equals a constant. That's not what's going on here. We're really looking for this Lagrangian that has this form. Now, the Lagrangian is going to be a function, in the case of a robot, of your joint variables, but in your system, of your coordinates. And we'll call these coordinates, for an n degree of freedom system, generalized coordinates. And this n degree of freedom system obviously lives in an n-dimensional configuration space. So here's Lagrange's equations. What we do is we differentiate with respect to the Lagrangian a velocity term, and differentiate that with respect to t, subtract that from the Lagrangian differentiated with respect to one of your generalized coordinates. And that will be equal to a generalized force, that could be a force or a torque, applied onto that one particular coordinate. Here, it's worth noting that we have n coupled second-order differential equations. N, indexed by j, that's for each degree of freedom of the system. So here, tau sub 1 would be a force or torque applied to the first degree of freedom and so forth. And the fact that it's coupled, what that means is if you have, let's say, an n revolute system, theta 1, theta 2, and so forth, even though the first differential equation, you'll be doing these calculations with respect to theta 1, there can be theta 2, theta 3 terms appear in that first differential equation. In other words, coupled differential equations are ones where variables from all the different coordinates appear in all the equations. Again, we should stress that this is a function of the joint angles and joint velocities. Your L is a function of Q and Q dot, where the right-hand side, that's your applied torque onto the jth Q or Q dot variable. Finally, when you end up with your equations of motion working out from your Lagrange's equations, you still need two sets of initial conditions, usually those on position and those on velocities, as well as what your torque inputs are, in order to solve your differential equation. In the examples that we're going to show in the class, we're just going to assume this will be equal to 0, just to make things easy for the explanation. It's also worth noting that I called these initial conditions because it was Q of 0 or Q dot of 0. You really could have Q of any point in time, Q dot of any point in time, but it makes sense to start with time equals 0, your initial conditions.